All right, I think most of us have joined now. We can get started. So just to have a recap, this bootcamp will be focusing on data structures and algorithms. And then we'll have looked at data structures in day 1 and day 2. That was Monday and Tuesday. And today we're going to look at algorithms. So yeah, please stay tuned. You're most welcome. We're getting started now with algorithms. Moving forward, today we shall have the theoretical session, and then we shall have the practical session tomorrow. A link will be shared for the challenge. Thank you all for joining. And once again, my name is Daniel Afedra for those that are joining for the first time. And I'm joined with two of my colleagues, Lynn, who probably has been communicating with most of you, and then Oghomwen from Nigeria, who has been giving us the content concerning data structures and algorithms. And just as a reminder, please share your questions in the chat, and feel free to share any thoughts or ideas that you'd like to be talked about in this particular bootcamp, and we'll do our best to address them. So I would like to then welcome you all, and also to welcome my colleagues. So yeah, let's just get started, IG. Yeah, once again, we have a global health hackathon happening in March 19th to 20th. It's a 2-day hackathon, and there are a lot of cash prizes for you, also solving real-world problems and meeting the Tunga community and other communities at large. Yeah, so please endeavor to register. The links will be shared with you as we have done in the past in the chat. So please check the chat and you'll find the link to the hackathon, and also the link to join Tunga and Tunga Academy with a Tunga testing site. So that will be shared with you in the chat. And then we'll also have a Tunga Ask the Expert Tuesdays, where we invite experts in particular topics to come and discuss with you what the experience is and share experiences with you. And so this coming Tuesday, which will be the 1st of March, we are hosting Subomi Olwalana on the Tunga Ask the Expert Tuesdays. So please feel free to join us for this event. So he'll be talking more about open source webhooks and then Convoy webhooks and working with APIs and also other dev tools. So please feel free to sign up. We shall still be using Zoom, and the link is already in the chat. You can check that out, and make sure to register for it, because there's also a lot of interesting stuff that will happen on that session. And now I hand over to my colleague, Oghomwen, who will be taking us through algorithms today. IG.
Hey people, welcome to the Algorithms Bootcamp. Interesting stuff for today. Most of us have been looking forward to it. So I already have a raised hand. Omotayo, do you want to say something? Let me.
You can unmute and speak, Omotayo.
Yeah. Yeah, I think otherwise maybe I'll just carry on. Omotayo, when you're ready, maybe leave us a chat or say something, yeah? Awesome. So for today, we're looking at algorithms. Particularly today, we'll look at some theoretical concepts around algorithms, and then tomorrow we'll get right into some practice, and then get our hands, I won't say dirty, but just get our hands into some practical aspects of algorithms, especially around understanding the performance of algorithms. All right, so the context for this really is, firstly, understanding that algorithms are extremely useful tools used to accomplish carrying out tasks. Algorithms are often elegant and incredibly useful for accomplishing tasks. They can save lives, they can make things easier, and they can conquer chaos. Knowing how to create well-optimized algorithms and understanding their implications is extremely important for software engineers, because if your algorithms aren't optimized, or if you don't understand the implications, you could get very bad results. And so it is important to understand algorithms, how they're optimized, and their implications. Okay, moving on. So I'll do an introduction in about a couple of slides. So many of us have heard of the term algorithms. I mean, almost everyone in this room should have at one point or another in their lives heard the word algorithm. You may have heard the term algorithm very recently, whether it was online or perhaps it was in some conversation about technology. It's a word that gets thrown around a lot of times, but we need to understand what it means exactly. All right, so just go through this video and uh, somebody said no audio. Right. Just saying that. Okay, so let me reshare. I think I didn't share the audio. Stop.
You may have heard the term algorithm.
Is there audio now?
You may have heard the term algorithm recently, whether it was online or maybe in some conversation about technology. It's a word that gets thrown around a lot, but what exactly does it mean? Well, simply put, an algorithm is a set of steps used to complete a specific task. They're the building blocks for programming, and they allow things like computers, smartphones, and websites to function and make decisions. But in addition to being used by technology, a lot of things we do on a daily basis are also similar to algorithms. Let's say you want to make some spaghetti. In order to do this successfully, there's a certain set of steps you need to follow in a particular order. First, you need to boil a pot of water. Once it's boiling, you then add the spaghetti and cook it for a set amount of time, stirring occasionally. Once it's finished, you drain the water and then it's ready to be served with a sauce of your choice. That entire process is actually an algorithm. Because you followed those steps in that order, you reached your desired outcome, a delicious pasta dish. But if you were to make a mistake, say over or undercooking your noodles, it probably wouldn't be as good. Programs work in a similar way. Their code is made up of algorithms telling them what to do. Let's say that we want to use a navigation app to get directions. When we punch in a destination, the app uses an algorithm to look at the various available routes. Next, it uses a different algorithm to check the current traffic. And then a third one takes that information and calculates the best available route. All of these algorithms are built right into the app's code. If there were any kind of error in that code, the app wouldn't be able to follow these algorithms correctly, meaning you wouldn't receive your directions. Both of these examples show how both humans and computers can use algorithms to perform everyday tasks. The difference is that computers can use algorithms and calculate things better, faster, and more efficiently than we can. Technology is only going to continue to evolve and get even better at what it does. As long as coding and programming continue to be used, algorithms will be at the heart of these technologies, guiding what they do and how they do it.
GCF Global, creating opportunities for a better life.
Awesome. So we know that algorithms from the video, I hope everyone's able to follow. We know that algorithms are simply a set of steps that we use to complete specific tasks. And so most apps that we use or most apps that we build typically incorporate a couple of algorithms to achieve the complexity of the features that we use on the app, right, or on the apps. Yeah, and algorithms are basically the building blocks for programming, and they allow computers, smartphones, websites, think of anything that is digitally functional. They allow those things to function and make decisions. In addition to being used by technology, a lot of things we do on a daily basis are very similar to algorithms. So typically when we make decisions in our daily lives, we go about it in a pattern similar to what we see on the screen. So we typically start out at the beginning, and we start to go through a couple of steps, and we hit points that we can refer to as decision points, where we decide what's next based on the options available to us, and then we continue based on that, and also end up at our expected output. So imagine something like going to school from your house, and then say you wanted to achieve the task of actually buying school supplies, for example, pens, right? Eventually, you start out from your house and you stop at a shop, and at that point, there's a decision. If they have pens, you buy pens. Otherwise, if they don't have pens, you still continue on your way to school and eventually get to school and maybe find a substitute along the way using another algorithm, either by asking a friend or asking a teacher or something else. So typically in our everyday lives, we use algorithms without even knowing it to process the tasks that we carry out. And sometimes we find that we do something, and over time, we start to optimize it. For example, many of us carry out our laundry, right? And sometimes we do it in maybe 2 hours. And another day, you might find out that if you maybe, instead of washing all your clothes in a non-sequential order, you wash the shirts first, and then you wash the pants next, you might find a system that helps you optimize how you do your laundry. And so in that case, you would have optimized the algorithm of doing your laundry. And that is something that is very similar to what we do in computer science and programming. We start out with an algorithm, and we then analyze it and see how we can optimize it, and also to ensure that we are getting the specific consequences that we intend algorithms to achieve. All right. So let's say, I mean, from the video, just recapping what was in the video. Let's say you want to make some spaghetti. In order to do this successfully, there's a couple of steps that you follow in a particular order. First, you typically boil water, and once it's boiling, you then add the spaghetti and cook it for a certain amount of time while you're stirring it occasionally. And once you're done boiling, you drain the water and then you serve it with the sauce. Other people will take another set of steps. For example, put in the water in the pot and they don't wait for it to boil. They just pour in spaghetti and allow the water boil and spaghetti cook all at the same time. That's another set of steps for cooking spaghetti. So whichever way you cook it, typically if you follow it from time to time, maybe every time you cook spaghetti, it definitely is called your algorithm. And there's also stuff like cookbooks, for example. It simply is an outline of steps to cook a certain dish, and that in itself is an algorithm. Uh, so yeah, this is a visualization of what we explained in this slide. You put spaghetti in the boiling water, you occasionally stir it, and then once you're done cooking to your desired level, you then drain the water and then serve it with a sauce that you are very okay with. Yeah. Yeah, so the entire process is an algorithm, like I mentioned already. And because you follow the steps in that particular order, you typically would reach your desired outcome, a delicious pasta dish. But if you ever made a mistake, like maybe overcooking or undercooking your noodles, it would not be as good as you want it. And so it's a similar scenario we have with programs. Their code is made up of algorithms telling them what to do, how to do it, when to do it, and all that information. And because I mean, everyone can attest to the fact that technology is an ever-growing field, and because technology is an ever-growing field, it will continue to evolve and get better at things that it does. For example, a technology that's continuously improving at the very moment is self-driving for cars. And we're starting to see cars that can drive themselves already, but there's still a lot of gray areas around how to optimize algorithms that allow cars drive themselves. There've been a couple of incidents where cars cause crashes while they're driving themselves, and those crashes uh, can be traced back to the fact that the algorithm malfunctioned, or there's still some questions around how algorithms are able to properly identify uh, people, pedestrians on the road, such that they don't run into pedestrians. There's a couple of questions coming up around the algorithms, for self-driving cars, and those technological applications will still continue to evolve and even get better. And in that sense, the algorithms will keep getting better. And as long as coding and programming continue to be used, algorithms will be at the heart of every technology, guiding what we do and how it's done. And so let's look at practical implications of certain algorithms, just to drive home the point of how important algorithms have become in our lives. An incident happened where the British pound dropped by 6.1% in value in a couple of seconds on October 7, 2016, partly because the currency trading algorithm triggered a couple of trades, and that caused a drop in the pound. And the algorithm took that decision entirely on its own. And you can see how massive the implication was for a currency to drop its value by 6.1%. All right, another real life scenario we can see of an implication is that Microsoft engineers created a Twitter bot called Tay in spring. I don't think it's this past spring, maybe a couple of springs ago, and in an attempt to chat with millennials by responding to their prompts. But within hours, they started spouting racist, sexist, Holocaust denying tweets based on algorithms that it's learning, based on algorithms that had it learning how to respond to others based on what was tweeted at it. And so the implications of the algorithm were not the desired outcomes, and they had to pull that chatbot. Another example, I have a couple. I don't think, maybe I'll not go through everything, but let's just see some more. Facebook tried to create a feature to highlight trending topics around the site in people's feeds. First, it had a team of humans edit the feature, but controversy erupted when some accused the platform of being biased against conservatives. And so Facebook turned the job over to algorithms, only to find that they could not discern real news from fake news. And so Facebook couldn't come up with an algorithm to help them differentiate between fake and real news. Yeah, and then let's move on. Maybe we can look at one more. Uh, okay, which one? Let me see which one is very interesting. Okay, yeah, this one is extremely interesting. Well-intentioned algorithms can be sabotaged by bad actors. And so this is one area to also look at for us developers who come up with algorithms. Sometimes our algorithms can be altered to do what they were not intended to do. For example, an internet slowdown swept the east coast of the US on October 21, 2016, after hackers bombarded DNS, an internet traffic handler, with information that overloaded its circuits, ushering in a new era of internet attacks powered by internet connected devices. This after internet security expert Bruce Schneier warned in September that someone is learning how to take down the internet, and the abuse of Facebook's news feed algorithm and general promulgation of fake news online became controversial as the 2016 US presidential election proceeded. And so this is a classic example of someone taking advantage of an algorithm and understanding how it works to sort of cause it to do something that wasn't the original intent of the algorithm. All right, I hope everyone follows up to this point. Any questions so far? Questions, anyone? Yeah, okay. All right, so let's get into some more interesting things. Algorithms, what are the characteristics of an algorithm? What makes an algorithm in itself? Firstly, algorithms should be unambiguous. An algorithm should be clear. It should be very evident what an algorithm is supposed to do. There shouldn't be any form of ambiguity around an algorithm. It should be clearly understood. It should be something that can be explained and something that can be seen to give its desired outcome. Each of its steps or phases and their inputs and outputs should be clear and must lead to only one meaning. So an algorithm should always have a clear, consistent set of inputs and outputs and set of steps also. Yeah, and then the second one also is an algorithm should have 0 or more well-defined outputs. Inputs rather. The inputs for an algorithm should always be well-defined. There should be no ambiguity around what an algorithm takes in as inputs. Outputs an algorithm also should have 1 or more well-defined outputs and should match the desired outputs every single time. An algorithm should also have finiteness, which means an algorithm must always terminate after a finite number of steps. An algorithm must always terminate after a finite number of steps. There's a beginning and an end for an algorithm. Also, an algorithm should have feasibility, which means an algorithm should be able to be used with the available resources. that it's being developed for. So you cannot develop an algorithm and run it in a system without available resources. It would simply not work. An algorithm should be independent, which means an algorithm should have step-by-step directions, which should be independent of any programming code, which means that algorithms can be implemented in any programming language. So an algorithm is code agnostic. If I write out an algorithm, it's something that in every language anyone should be able to implement, and which is why it's important for every developer, irrespective of whatever language you write or coding, to understand algorithms. Okay, so from a data structure point of view, like we've been seeing from the last 2 days, a couple of important algorithms can be abstracted or can be drawn out of what we've talked about. So for example, the search algorithm. It's an algorithm for searching items within data structures. So you can imagine how important it is to be able to quickly search for things within a data structure. And so that algorithm is an important category. Also, a sort algorithm is typically used to sort items in a certain order. And sometimes it's a desirable thing to be able to sort a collection of elements. Also, imagine that you have to add elements to a collection, and the algorithm for inserting elements into a collection typically should also be very optimized. And so that's one important category of algorithms. The update algorithm also for updating elements within a collection. That algorithm is also a very important one within computer science. And then delete algorithm. Uh, Simply is the algorithm to delete an existing element from a data structure. So these are important categories of algorithms that search, sort, insert, update, and delete algorithms, and see how they perform. And that would typically also inform you about when it is best to use certain data structures. And so the data structures and algorithms definitely go hand in hand. All right. So then let's talk about how to write an algorithm. How do you come up with an algorithm? Firstly, there is no well-defined standard for writing algorithms. Rather, it is a problem and resource dependent activity. Algorithms are never written to support a particular programming language or particular programming code. As we know, all programming languages share basic code constructs like loops, for example, for loop, while loop. These are things we're familiar with from any language you're coming from. And every programming language also supports flow control statements like if and else, etc. A couple of branching statements exist in every single language that exists as a programming language in the world today. These common constructs can be used to write an algorithm. Abdullah Brima, you're asking why shall we deleting an existing data structure? I think what you're trying to ask is why do we? No, so when I mentioned the delete algorithm category, I don't mean deleting the data structure. I mean deleting elements or items within a data structure. Say, for example, you have an array and you need to delete an item out from the array, and you typically want to know how long or how fast that operation will take. So that was, I mean, does that answer your question? Hi, Abdullah. Oh, awesome. All right. So continuing from what I said, secondly, yeah, I first said that there are no well-defined standards for writing algorithms, right? Rather, it's a problem and resource specific activity. Algorithms, again, second point is algorithms are never written to support any programming language because all programming languages ideally share basic code constructs like loops and flow control statements like if else, such that we can use those constructs to write algorithms. And then thirdly, we write algorithms in a step-by-step manner, but it is not always the case. Algorithm writing is a process and is executed after the problem domain is well defined. That is, we should know the problem domain for which we are designing a solution. So sometimes we do not come up with an algorithm in a step-by-step manner because we do not fully understand the problem domain. And so maybe we start out with writing out something. Initially, it's not complete. And then the more we get an understanding of the problem domain or area, the more we then start to adjust what we have on ground eventually before we come up with an algorithm. Yeah, and many times we find that we have to make changes to even existing algorithms, right? And so that's typically the case. The I mean, for some of us who have worked on projects, or if not or everyone already, there's a part of the project called requirements gathering. And typically in that part of the project, we try to understand the problem domain and typically well define the problem. And so in that meeting or conversation, we can already start to come up with an algorithm. Typically, maybe not step by step. Maybe we'll come up with something, and then the business team comes back and adjusts the problem specifics, and then we also have to change something within our algorithm. So eventually, we then arrive at the final algorithm. And so yeah, we can acknowledge that sometimes we don't come up with it at a goal, you know. Yeah, so let's try to, or I mean, all this talk about algorithms, let's try to learn algorithm writing by using an example, a really simple example. Let's try to write an algorithm to add two numbers. All right, I already have a slide that outlines it. So typically, if we were to add two numbers, let's just assume the numbers are integers, right? We start out by declaring three integers. Why? Because two of those will be the numbers we need to add, and the third integer will be where we store the result of the two numbers that we add. And so we define the values for A and B being the two numbers that we want to add in the third step. In the fourth step, we then add those two numbers, A and B. In the fifth step, we store the output of step 4 into the integer C. And then the sixth step, we print out the value. And then at the seventh step, we're done. So far, so good. This is the typical algorithm for adding two numbers. If everyone understands this to this point, that'd be great. But if anyone has a question, please raise your hand, drop it in the chat. And then I can see if I can answer. Maybe, I mean, is there a way to give a thumbs up on Zoom? I'm not sure. Yeah, so you can give me a thumbs up just to be sure everyone understands to this point, especially for anyone who doesn't have a programming background. Yeah, just show me that you follow. Awesome, Gerald, your hand is raised. Maxwell, so I'm just going to unmute, allow you to talk. Gerald. Gerard, do you have a question? Gerard, you can ask your question. Nobody has spoken in the entirety of this boot camp. So Gerard, you'll probably be the first to speak. Otherwise, drop a question in the chat. Okay, so I think maybe I can go on from here. So there you have it, a simple algorithm to add two numbers. Yeah. And then now, the reality of it is that we design an algorithm to get a solution to a problem, but we find that a problem can be solved in more than one way. For example, I just defined that in the previous slide, it was a way to add two numbers, but definitely I'm certain someone else can come up with another way to add two numbers that would not be this exact algorithm. And so what we have in reality is we can get that we can get multiple algorithms to solve a single problem. We can get multiple solutions to solve only one problem. Hence, many solution algorithms can be derived for a given problem. And then the next step would then be to analyze those proposed solutions and then see how we can implement the best suitable solution. And that is one important step in algorithm design. It's being able to implement the best suitable solution. Even if you have multiple solutions, you typically want to implement the most optimized solution that gives the best results in most cases, if not all cases. And that brings us to an interesting part of games and the conversations around it, which is algorithm analysis. Okay, and what is algorithm analysis? Firstly, let's talk about why we need it. I'd already alluded to the fact that because we can come up with multiple solutions to a certain problem, we typically would have multiple algorithms, and we definitely can choose the most efficient in that sense. If I can already use the word efficiency, we can choose the most suitable algorithm for the problem. And so there's the need to further analyze it so that we can determine what the best solution is. So algorithms are often quite different from one another. And though the objective of the algorithms may definitely be the same. For example, we know that a set of numbers can be sorted using different algorithms. I think we'll look at a couple of sorting algorithms tomorrow. If you don't already know any sorting algorithms, that's totally fine. We'll look at some of those practically tomorrow. Yeah, and then a number of comparisons is typically performed by one algorithm, and it will vary from other algorithms for the same input. Typically, how one algorithm will compare the values to sort through a collection of elements will be different from how another algorithm would also do the comparison. Hence, time complexity of those algorithms may differ. At the same time, we need to also calculate the memory space required by each algorithm. Now, below there's an image that you can see. It's a sort algorithm in visually representing a sort algorithm. The first, this algorithm solves the task of sorting an array in 4 steps. You see, in the first step, what it does is it brings the -2 forward to the first point and moves -1 to the point where -2 is in. And by the 4th iteration of this algorithm, we realize that the array is sorted. And this particular sort algorithm is called insertion sort. I will see some of it tomorrow. All right. All right. What else? Algorithm complexity. Give me a second, everyone. Apologies, everyone. Just give me a second. I'm resolving a technical issue.
And as IG comes back, please check the chat for the links to the different channels. The first one is to join Tunga. The next is for the Tunga Academy. And then the Tunga testing platform where you can do tests to test yourself in the different programming languages. And then we also have a global health hackathon, which is running next month on 19th. Please feel free to register. And then next Tuesday, we have Tunga Ask the Expert. The link is also available in the chat. Feel free to register and join us. Meanwhile, please submit your questions or any queries you may have in the chat and Q&A respectively, such that we can address any issues. And if you'd like to speak, please raise your hand and then unmute when you're allowed to speak.
Sorry, people. Yeah, apologies, I'm back. So yeah, algorithm complexity. Everyone follows from this previous slide. Yeah, the need for analysis. If anyone needs me to recap this, you can ask in the chat. Otherwise, I would go on to what I'm about to speak on. All right, so algorithm complexity, which is a metric for determining the best algorithm to pick out of a set of algorithms that we might have to solve a particular problem. Complexity of an algorithm can typically be analyzed using 2 perspectives. The first one being time and the second one being space. And what's really that is that time complexity is a function describing the amount of time that an algorithm requires to run in terms of the size of the inputs. Please take note, take note in this slide particularly, that time complexity is describing the amount of time required to run an algorithm, not necessarily in terms of seconds or minutes, but in terms of the size of the input. And so time can mean the number of memory accesses performed, the number of comparisons between integers, for example, the number of times some inner loops take to execute, or some other natural unit related to the amount of real time that the algorithm will take. Right. So we'll definitely look at examples of this. All right. And then space complexity, it's a function describing the amount of memory that an algorithm will take in terms of the size of the input to the algorithm. We often speak of extra memory that is needed, not counting the memory needed to store the input itself. Again, we use natural but fixed length units to measure this complexity. But again, importantly, space complexity is sometimes ignored because the space that is used by an algorithm is typically very minimal and it's not obvious. Many times it's not obvious. However, sometimes it becomes an important issue, as time complexity for algorithms that usually memory or that typically memory, should I use, will intensive be the right word, or algorithms that typically use a lot of memory in processing the inputs, space complexity can become very important to measure. But many times we find that we are particularly dealing with algorithms that where the time complexity is more important. All right, so let's define this again in terms of size of inputs, just to understand it a lot better. Omota, you want to ask a question? You can go ahead and unmute.
Hello.
Yeah, what's up?
I want to say that I am seeing the time complexity and the space complexity as a proportional relationship. So, like every time we have a time issue, like the increased number of time that is needed for an algorithm to run, there will be a directly proportional increase in the space of that same algorithm. However,
Not
is there
necessarily.
any
Not
so is
necessarily.
there
Have you heard of merge sort? Ever heard of merge sort?
yes,
It's an algorithm
merge
that's the
sort, yes,
fastest sorting algorithm, but then it uses so much space.
without the time being proportional to it.
The time is the
Okay.
shortest time it takes to sort any collection. But for bubble sort, it uses the smallest amount of space, but it's way slower than merge sort. So it's not always proportional. Space complexity and time complexity are never really proportional. Sometimes you find a very fast algorithm using more memory than a slow algorithm. Yeah, but go on with your question now. I just wanted to say that first.
Okay, like clarification I was trying to wrap my head around.
Come again?
Hello, I think that's the clarification I want to wrap my head around. Like I was
Okay,
thinking
okay.
that
So
the space
I will
complexity is
show you.
actually directly proportional to the time complexity.
No, it never is. It never is. So
All right.
tomorrow I would show you the four sorting algorithms, and then you see how they work, and actually see which one uses. You see that the fastest one uses like the most memory. Yeah. So yeah, they're never proportional. I mean, in some cases you can find that yes, you do use less memory for faster algorithms, but there's never any correlation. Never. All right. Anybody else? All right. Yeah, somebody's asking, do we need to pay more attention to space complexity for recursive algorithms? Well, it then I wouldn't say yes. Neither would I say no, because I mean the algorithm itself might not use up too much space, but in terms of recursion, I mean maybe what you're asking is if recursive algorithms use more memory than non-recursive algorithms. And that would typically be a yes, because you're doing multiple function calls. However, the data structure that backs recursive functions in memory is called a stack. And so sometimes you'd have heard of something called stack overflow, right? And what a stack overflow, what typically causes a stack overflow is when you have functions, a number of function calls that are happening, and then there's no more memory within the stack to store those function calls. And so you arrive at a stack overflow because they have run out of memory to store the function calls. But then again, a stack is the most efficient thing for function calls, because think about it, the stack is last in, first out data structure, right? And so you want, for a recursive function, because you want the last method called, hello? Ramon, do you follow? So in any case, I was saying it's because a stack is a last in, first out data structure, right? You want that the last function called should be the most recent, or the first function to return. And so you find that the first function that was called would be the last to return, and that's typically how a stack executes. All right. Alan is saying the most common cause of stack overflow is excessively deep or infinite recursion, in which a function calls itself too many times that the space needed to store the variables and information associated with each call is more than can fit on the stack. Yeah, typically, yeah, that's the most common. However, how do you determine that you are going excessively deep into a recursion? So you never should design an algorithm that has infinite recursion. And one criteria, or one requirement typically for coming up with recursive algorithms or the recursive functions is that there's a stop condition. And so you'd expect to always hit that stop condition. Otherwise, if it's going to infinitely be recursive, then you definitely maybe eventually hit a stack overflow exception. Yeah, Ramon, you asked, so the issue with recursive functions is the number of function calls on the stack and not the space for storing variables. Got it. Yeah, well, it's both really, not it's both. So because the recursive functions, the calls on the stack also uses space to store variables. That's it's part of the issue, but the variables are not stored on the stack, ideally. It's the function calls that are stored on the stack, but then you can run out of memory for the stack because you have variables being stored in the memory. For different programming languages, they call it what's the one? Which one can I remember? A heap, yeah. If you've ever heard of a heap, typically a heap is used to store objects and variables in that sense, and the stack is, I mean, if I'm remembering correctly, the stack is what stores the function calls. And so typically the number of function calls on the stack in conjunction with the space consumed on the heap would result in the stack overflow exception. But you can look into this more. Just check out some more materials I can explain that would give you a deep dive into explaining how memory works. Awesome. All right, so yeah, now let's talk about algorithm complexity So Tajudin, you're asking, in the stack, the function are garbage out once the function return. How do we achieve stack overflow if every function are pop out before the next one? For recursive calls, Motayo, the function does not pop out before the next one. For recursive function calls, you keep calling the functions recursively until you hit the stop case. When you hit the stop case, then the stack starts to return the function calls on top of the stack. That's why it's a stack. It's not like every call, every function returns immediately. It doesn't return every function. So the stack returns the last function called first up until it gets to the end of the stack. So when you first make the first function call, the first function call doesn't return. If you make the second one doesn't return. If you make the third one doesn't return. By the time you maybe say, assuming you then hit the stop case at the fourth call will return, then the third call returns, then the second call returns before the first call returns. So that's how the execution goes. All right. So that's why it's, that's why it's typically stored on a stack. Mota, do you understand that? Okay. Awesome. All right, so let's move on from this. Okay, so we're still talking about algorithm complexity. Suppose X is an algorithm, the algorithm in question, and N is the size of the input data. The time and space used by the algorithm X are two main factors which define the efficiency of the algorithm X. The time factor we first said is measured by not necessarily counting in terms of minutes or seconds, but by counting the impact in terms of the size of the input data. That's one way to measure the algorithm. There's several other factors, but in general, we measure the time factor by counting the number of key operations, such as comparisons, for example, in a sorting algorithm. Space factor is measured by counting the maximum memory space required by the algorithm. And the complexity of an algorithm, Fn, gives the running time and or the storage space required by the algorithm in terms of n as the size of the input data. All right. Algorithm analysis is the process of analyzing. Chima, your hand is up. Okay, let's hear Chima. Chima, you can go. Chima, you can unmute and speak. Okay. Chima, I don't hear you, so maybe you can leave me something in the Q&A section or drop a chat. All right. So analysis of algorithm is the process of analyzing the problem-solving capability of the algorithm in terms of the size, in terms of the time and the size required, the size of memory for storage while implementing or during implementation, or typically during the run time of the algorithm. However, the main concern of analysis of algorithms is the required time or performance. So mostly we see that what we're almost always concerned with in terms of analyzing algorithm is really the time complexity, or otherwise known as or otherwise we refer to that as performance of the algorithm. All right. Um, okay, so moving on. And there are two types of analysis. Yeah. The first one is that, or firstly, I would say that the efficiency of an algorithm can be analyzed at two different stages. Firstly, before implementation, and secondly, after implementation. And there are two types of analysis. One is called a priori analysis, which is the analysis that is performed prior to running it on a specific system. This analysis is a stage where a function is defined using some theoretical model. Hence, we determine the time and space complexity of an algorithm by really just looking at it rather than running it on a particular system with memory, processor, or compiler. So this analysis is done not necessarily with any system in place. We do it by simply looking at the algorithm and analyzing it mathematically, really. A posterior analysis is what we do when we perform an analysis of an algorithm after we've run it on a system, and it directly depends on the system resources and changes in the system from one system to another. Yeah, but a priori analysis is typically what we use as computer scientists because it will be almost impossible for you to test your algorithms on all systems that it will typically run on. You never know what systems your customers or your clients are going to run your program on, and so you typically want to analyze your algorithms irrespective or without regard necessarily to the system by doing a very objective analysis. And a priori analysis is typically the best way to do that. Okay, so let's look at an example and analyze quickly analyze an algorithm, using a priori analysis, so we understand it really. Simple example: say you are given an array A and an integer X, and you have to find if X exists in the array A. A simple solution to the problem is to loop through the whole array and check its value within the array to see if X equals any of the elements within the array. Now, if you never, or if you come from any programming language background, yeah, I mean, I think this code may or should ideally be simple enough for everyone to understand. However, maybe I'll just explain line by line to show you what's going on here. So on the first line, there's a for loop. And what this for loop ideally is doing is going through every single element or within the array one at a time. So assume the array is the array you see to your right with values 1, 3, 5, 2, 4, right? And then the for loop, which is the first line, what it's going to do is first pick out the element at position 0. Next, it picks out the element at position 1 up until it gets to the last element. And so that's what it's doing. It's just looping through the array and picking one element after another, one after another, really. And if the next line is what it's doing is it's typically doing the comparison, checking the value at each position and checking if it's equal to the value X that we need to determine determine whether a X exists in the array or not. And so what will happen is, for example, say X was 3. At the point where I is equal to 0, we do the check if AI, which is I is equal to 0, AI will give us the value 1. And what we do at this point is we check if 1 is equal to 3. If 1 is equal to 3, we return true, otherwise we return false. In this case, we know that 1 is not equal to 3. And so what happens is the if statement passes the control back to the for loop. And then we then check the next position. I becomes equal to 1. We then check the value at A1 is 3. Is 3 equal to 3? We then say yes, and then the loop returns true. Now, for a case where X, for example, is the number 6, we know that X is not within the array that we're comparing. or checking. So what happens is the for loop is going to run from the first element all the way to the last element and find out that X is not within the array, or the array doesn't contain X, and eventually the algorithm will return false. All right, and so let's analyze this algorithm based on what I've explained now. Yeah, so each operation in a computer takes approximately constant time, right? But let each operation take C time. Each operation that takes constant time takes C time. The number of lines of code executed actually depends on the value of X. And as I had mentioned earlier, if X does not exist in the array, then the for loop is going to go through the whole array from beginning to end, and the number of operations that will be executed will depend on the size of the array. The number of comparisons that we then have to do will depend on the size of the array, right? And so during analysis of this particular algorithm, mostly, or during analysis of any algorithm, mostly we'll consider the worst case, or rather the worst case scenario. That is, for example, for this particular example, when X is not present in the array A. And in the worst case, the if condition will run n times, where n is the length of the array. And so again, just reiterating, if the value that we're checking for is not within the array, that's the worst case. It means the algorithm is going to run through the entire array, and the length, assuming the length of the array is n, it means the comparisons we'll do within the algorithm will be n number of comparisons. So in the worst case, the total execution time will be n times constant time plus constant time. And n times constant time is for the if condition, because the if condition is constant. The check to check if the value is equal to X is constant. But then we have to do that n times, which is why the if condition will take n times C time to execute. And the C is for the return statement, which is constant. So we either return true or false, and we do that once. And because we do that once, that's constant time. And so this entire algorithm will have an execution time of n times C plus C. And eventually, we can see that the total time depends on the length of the array. And if the length of the array will increase, then the execution time will also increase. If the length of the array decreases, the execution time will also decrease. Now, if we're talking in terms of big O, I'm just preempting myself really, in terms of big O notation, eventually this evaluates to big O of n. Reason is because when we talk about formulas like this, what we consider mostly is the most prevailing value, or the value that has the highest impact or within the formula. And so we see that n is the value that has the most impact on this formula. And so we can ignore C and the other C, which are constants, really, they never change. And so because n is what changes and will impact the entire performance of the algorithm, and then n is what really is the runtime of this algorithm. But we'll see why that is in a short while. Anybody has any question about this slide, about how we analyze the algorithm? Does everyone understand how we arrived at this conclusion? Was this a good example? Please give me some reaction. Anyone else? Anyone has a question? Just waiting for questions for 1 minute, because this is really important in terms of understanding algorithm analysis. Because it's the most simple example I could find So I want everyone to be able to understand it. All right, Alan says to explain n times c plus c. Awesome. I'll go ahead and explain that again. Alan, if you look at the code on the left, right, the first line is the for loop. Okay, and if you're familiar with for loops, you know that the for loop will run n number of times, n being the length of the array, right? And so if the for loop runs n number of times, and then we go to the comparison within the for loop, we see that the if comparison typically runs one time, and so that's constant. Yes, so that's 1c. The if statement is a constant statement. It's just one comparison. It's saying if this is equal to this, and so that's one comparison as an operation. But the for loop would run for n times, which is the length of the array. And so if you multiply the runtime of the for loop by the constant time it takes to do the check, that's n times c. Okay, and then the other c is for either of the return statements. Because we're going to hit the return statement once, and we're either going to return true or false, those are also constants, because we're going to reach those blocks or those statements once within the algorithm. And so if we return a true, that's one constant operation, or if we return a false, it's one constant operation. And so the other c is either the true or false. And so that's how we have n times c plus c. Alan, does that answer? Awesome. All right. And then again, maybe I'll just mention, yeah, that eventually the formula in terms of talking about big O, which we'll talk about in a couple of seconds or minutes, the formula evaluates to big O of n, because n is the most prevalent value, or the value that has the most impact on the algorithm. And so that the effect of n, because it's what it affects the entire performance, we say that in the worst case, the algorithm will run at the runtime, or the time it will take for the algorithm to run, is n, or big O of n. But big O is also refers not necessarily, not entirely to the time it takes to run, but also speaks to the growth rate of the algorithm in terms of number of inputs. All right, and I think that's the next slide. So, okay, firstly, let's talk about some mathematics, which is something you can't run away from as a computer scientist. Yeah. So asymptotic analysis. What this is one way to analyze algorithms. And remember, we talked about a priori analysis. An a priori analysis, we said, was analysis that's performed prior to running an algorithm on a specific system. So this is analysis we do irrespective of a system. Analysis we do by simply looking at the algorithm and theoretically analyzing the algorithm to determine its efficiency. All right, and a priori analysis is one way to actually do it is to do asymptotic analysis. Asymptotic analysis. All right, and what that is really is that asymptotic behavior of a function fn refers to the growth of the function as n gets large refers to the growth of the function, keyword here being growth, as n gets large. And so we typically ignore small values of n since we're usually very interested in estimating how slow a program will run on large inputs. That is not to say that small values are important for certain algorithms. We want to always even check the performance of the algorithm at all values, whether small or large. But mostly, we typically would ignore small values of n and focus on situations where n becomes really large. And the good rule of thumb is that the slower the asymptotic growth rate is, the better the algorithm is. But that is not always true. It is not always true, but it is a good rule of thumb. There are situations where it's not true that the slower growth rate is typically a better algorithm. Maybe we'll look at certain situations like that in tomorrow's session. So for example, a linear algorithm Fn, which evaluates to d times n plus k, is always asymptotically better than a quadratic algorithm, which is c times n raised to the power 2 plus q. So we know that we can evaluate the first algorithm, or the first algorithm will typically take us less time to compute, or rather this is called them algorithms, entire functions really. The first function will take a shorter time to compute than the second function, which is a quadratic function. Yeah, and so if you've never really done any of these quadratic equations, quadratic functions, there's a course I recommend at the end that will give you a good head start into all of this. There's something called mathematics for computer science. It's a branch of mathematics, or it's a topic within computer science, specifically addressing certain mathematical concepts that's important for computer scientists, and just to understand the general concepts of computer science, and how to really communicate the ideas within computer science. And so I'd definitely recommend taking the course. Link is somewhere within the slides. We'll see that soon. All right, so notice I said the keyword on this slide was growth, and specifically growth as the input size becomes large. And so order of growth is how the time of execution depends on the length of the input. So remember when I first said that on this slide, because the length of the input n impacts the algorithm the most, the order of growth of the algorithm really is n. All right, so order of growth is how the time of execution depends on the length of the input. In the above example, we saw clearly that the time of execution is linearly or linearly depends on the length, depending on the length of the array. So Alan is asking, so we evaluate the performance of an algorithm in terms of the input size. Yes, that's one way to evaluate the performance of an algorithm. Yeah. Okay, so going on. Order of growth will help us to compute the running time with ease. We will ignore low order item. We will ignore the lower order terms, since the lower order terms are relatively insignificant for large inputs. We use different notations to describe the limiting behavior of a function. And let's look at those notations. These are asymptotic notations. In mathematical analysis, asymptotic analysis, also known as asymptotics, is a method describing the limiting behavior of functions. And asymptotic notations are also used to represent limiting behaviors of functions. And three important limiting behaviors are what we'll look at now. There's one more, which is called, there's a fourth behavior, but it's not on this slide. But these three are the most important, really. Yeah, and of the three, there's one that's also most important. Or maybe I'll just say the three are important, and there's one that's most important. So firstly, there's a worst case scenario. which is also called the asymptotic upper bound. If you've ever heard of big O, or you've been wondering about what big O notation is really about, it's the worst case scenario analysis of an algorithm, which is typically the maximum number of steps taken for any instance of size A for the algorithm to process any instance of size A. And so that is big O asymptotic analysis, asymptotic upper bound of any algorithm. The best case is called big omega, which is the asymptotic lower bound. In this case, we're thinking, what is the minimum number of steps taken for any instance of size A? Now, for this algorithm, the best case, who can already tell me what the best case is for this? Now, this algorithm can take one step to run. But who can tell me what the value of X would be for it to take one step to run? Somebody put an answer in the chat. Yeah, somebody says when X is equals to 1 in the first position. Yeah, that'll be the best case for this algorithm. So that is typically the big omega notation, in terms of big omega notation, which is best case for that algorithm, we'll be looking at the big O of 1, assuming X is the first value in the array. So the minimum number of steps it takes for any instance of size A to be processed is called the best case. And the average case typically is called the asymptotic tight bound, which is called big theta. It is the average number of steps taken for any instance of size A. And when the big O is equal to big omega, typically that's what we call big theta. All right. But the most important thing we'll pick out from this slide is the worst case, which is big O. And so we'll mostly focus on big O analysis of algorithms. All right. And so these are like the most popular complexities in terms of big O notation for algorithms, considering the input sizes. On this particular table, we're looking at when the input size doubles, what happens to the runtime. Now, for algorithms with big O of 1 complexity, if you double the input size, the runtime stays the same. All right. For algorithms of log n big O notation, if you increase if you double the input size for the algorithm, the number of operations only increases by a certain constant. And so there's an interesting video that I'll play in tomorrow's session just to really demonstrate how this works, or demonstrate an algorithm that has big O runtime of log n. And then for an algorithm with a complexity of big O of n, if you double the input size, the number of operations would double. And so that's why it's big of n. For an algorithm with big of n squared, if you double the input size, the number of operations would quadruple. For n cubed, the number of operations will get to 8 folds. For 2n, 2 raised to the power n, this is left for you to analyze. All right. Maybe not everyone can analyze that, but you can just try and do some research and determine what will happen if an algorithm has a complexity of 2 raised to the power n, and then we double the input size. Imagine imagine an algorithm. Just try to come up with an algorithm that would take that will run at 2 raised to the power n in the worst case. Let me see if I can come up with one as we speak. 2 raised to the power n, 2 raised to the power n. Yes, I know an algorithm. Ramon says 2 raised to power 2n. I'm not sure I understand that. So an algorithm, Ramon, maybe you want to speak up and explain it. But an algorithm that can take 2 raised to power n to run is Ramon, do you want to explain? Callisto says 2 raised to power n seems better than n raised to power 2. Yeah, well, until you do an analysis, you never really know. So if you're able to tell me what the effect of doubling the input size for that algorithm is, compared to what doubling the input size for an algorithm of n raised to power 2 is, then we can then say which is better. But at first glance, it appears to be that 2 raised to power n might be better than n raised to power 2. Okay, I think I'll just move on at this point. We'll have some limited time on the clock. Okay. Yeah, Callistus, you said take 3 for instance, 2 raised to power n equals to 8. 3 raised to power n raised to power 3. Yeah, 27. Yeah, so that's Callistus has done the analysis. Yeah, so everyone can look at the chart and see his illustration. Yeah, that gives an idea of which is better. All right. So I think we already even came to almost the end of the slide. So this is where I took some of the stuff you've seen on the slides from. When you get the slides, you can check out these links, really good sources. Okay, yeah, I think it's just you. So I'll just, because this is, you can just repost your chat to the entire chat room. Otherwise, maybe I should just already do that for you guys. Callistus, is that fine? Reposting your chat. Awesome. So yeah, so that was his claim, and this was his quick analysis, and so you can see that an algorithm that has 2 raised to power n runtime is definitely going to run faster than an algorithm with n raised to power 3. All right, something in the Q&A. Okay, that's Callistus again. All right, so I think it's now time for some questions and answers. Anyone has questions for me? Ramon says he doesn't agree. I think n raised to power 2 is better than 2 raised to power n. Ramon, according to the computation, apparently it looks like definitely is that 2 raised to power n is better than n raised to power 2. Ramon, do you want to compute those yourself and check it out? All right, anyone has any questions so far? Yeah, Motaya says the exponential increase, which might be bad. Yeah, well, it might be. Good thing you didn't say which is bad. All right, I don't see any. Okay. This do you mean an inverse log? When you say 2 raised power n can be expressed as a log function. Okay, Callistus, yeah, definitely check it up. So Ramon, do you have your answer now? Okay, I'm meeting Ramon. Ramon, Callistus has something for you. Or Callistus rather, Ramon has something for you. Ramon, you can go ahead and speak. Otherwise, Callistus, you can check the chat. Ramon also did his analysis.
Hello.
Hey.
Okay. Yes. So I saw the chart from Tayo. It's actually 2 raised to power n and not 2n.
Yeah, it's not too end.
So from the analysis I just showed on the chart, right? If we take 3 as an example, we take 3 as an example, 2, that's n squared, right? If you take
Performs better.
as an, yes, 2 raised to power n
Performs, yeah.
it gets what as the input
yeah.
group. It gets what? So for smaller sizes of n, n square might seem to be better, but once it keeps increasing, it gets worse.
Yeah.
So 2 raised to power n is, I think it's the worst actually of the in what is shown in this list.
Nice. So that's a situation where you see that one algorithm might seem better than another for lower input sizes. But then when the input sizes grows, then the other algorithm starts to perform a lot better. So that's a classic example. Yeah, Callistus, you see this? Callistus still here. Okay. Awesome. So it's all in the analysis, people. It's all in the analysis. All right. So I think I'll drop some links in the chat that you can pick up and look at after this. Let me look for those. Okay, so 2 links. I'll drop 2 links so everyone can look at this just to get their hands or just to practice more on or look at more questions that pertain to time complexity analysis. And then I had mentioned earlier that there's some mathematics that is really good for computer science. And so everyone should also check out this link. The Mathematics for Computer Science is a course from MIT. Was taken or was taught in spring. Was it spring or fall of 2010? It has some really good resources, gives you some foundational knowledge of mathematics that will help you excel as a computer scientist and a software developer or programmer, as well as also dives into asymptotics and gives some really good explanation. Also, Another course you can check out, which is also you can audit for free, is algorithm design and analysis on edX. So you can check out these 3 resources. Maybe you come back with questions for tomorrow. Tomorrow we'll look at, I think tomorrow we'll see a video of a live demo of an algorithm firstly, and then also a live demo of the, maybe, yeah, I think both are in one video demonstrating the efficiency of an algorithm. I particularly said that there was an algorithm that used more memory but was efficiently better than a certain other algorithm that used less memory. That's merge sort, again, something like bubble sort. So we'll look at that tomorrow, as well as also look at the live demo for the live demonstration of an algorithm that takes log n time. And maybe also, we'll also look at the analysis of the algorithms for the data structures in terms of retrieval, element insertion, deletion, and sorting. Yeah, well, okay. I mean, if you look at sorting algorithms, generally that takes care of that. But insertion, deletion, updates, and retrieval of elements from different data structures, I think we'll look at the algorithms for those and how efficient they are. Yeah, and also Ramon, you're asking if the course is free. Yes, it's MIT OpenCourseWare, and so the resources are available. Just check it out. You don't pay anything for it. Also, the course the course on EDX, you can take it for free. That means you can audit it, but if you need a certificate, then you have to pay. But I mean, you can just learn the content to start getting certificates. The knowledge is way more important than even the certificates. So just go ahead and check those out. Alrighty, I think we've spent a good time together today. At this point, I'll say catch you guys tomorrow. Catch everyone tomorrow.